Okay, let's get started, everyone. So today we will be discussing multimodal language models, so vision and language models. Before we do that, some logistics stuff. So we are in the process of grading your exams. We're hoping to finish by the end of this week, so you'll have your grades by then. Oh God! All right. So I hope I did test this in the morning and it worked. But please, if you're on YouTube and it's lagging, let me know. And possibly this resolution thing is, I don't know why it didn't come up this morning. But all right. So right, we will go over the midterm in class on Wednesday. I will just roughly go through all of the answers and try and highlight common mistakes that were made by students in the class. You'll also have quizzes from now till the end of the semester, one per week, and so be on the lookout. Tonight, the quiz for this week will be released. Okay, so with that, let's get started with the topic for today. So first, just as a demonstration, we are interested in models that can process both text and images and can understand and generate both text and images. So I wanted to just show the capabilities of like one of the state-of-the-art systems, which is GPT-4V, the Vision Augmented GPT-4. So I prepared a couple images here. This image is of a guy with a cone over his head riding a bike. Clearly a pretty unusual image. So let's see what ChatGPT thinks about this. So we can just say, what is going on in this image? All right, so a person riding a small bicycle down an alleyway with a large traffic cone placed on their head. It's a comical scene, likely meant to be humorous or absurd. The surroundings suggest an urban environment. The person is pedaling the bike. Does not look like they're pedaling the bike. It's not every day you see someone wearing a traffic cone as a hat, especially while riding a bike. Okay, so it exhibited some understanding of this bizarre image. We can ask it questions. Does anyone have a question they would like to ask about this image? That might be tricky to answer. Yeah. Well, let's say it should be answerable by the image itself, so not a subjective question. Okay, but I mean, like, we can't, I guess. All right, let's try it. How old do you think the person is? What do we think the person's age is based on this? I would say like 30s, 40s. Yeah? Okay. What? Yes. All right, let's see what happens. Ugh, all right. Is it going to give us a guess? An adolescent or young adult. All right. So that was a good question. This kind of behavior is often associated with those age groups. All right, let's see if we can ask for some more details. So it looks like these are socks or something on this guy's shirt. You can ask how many legs, maybe? How many legs are on the shirt? So there are 6 legs. How many legs are on the guy's shirt? That's a strange question. Okay, so it says that it has 3 visible legs, which is false. So you can see that the model has some degree of understanding of this image, but when queried with very specific details and asked like questions about them, it really struggles to answer. Another thing that these models struggle with is when there's a lot going on in the image. So here we just have one person with a background. It's a pretty tame image. I also had this other image where this man is holding up a book and there's a lot of writing in the background. There's a lot of things going on in this image. So let's see how well the model does here. What's going on in this image? So you can see that the generation speed is quite slow, and we'll get into why this is actually the case later on in the semester. All right, we have a classroom setting where a teacher is holding up a book titled Stars Beneath Our Feet. Wandering Stars by Tommy Orange. So it got the word stars, but messed up all the other words. The whiteboard behind him is filled with notes, including the word orange, suggesting the class may be discussing themes, literary devices, and the content of the book he's holding. There are students seated at desks. The one in the foreground seems to be listening to or reflecting the discussion. Okay, so maybe we can see how well this model can understand text in images and ask it, what are some words that are written on the right side of the image? Maybe that's a good question. List all of the words written on the board to right side of the image. Okay, wow, that seems quite correct, actually. Nice. It even completed these words that are off the screen. So it did much better than I thought. One other thing we can probably do is ask to compare both of these two images, because they're both technically in our prompt. So I could ask, are there more people visible in the second image than the first? So every time it is going to get slower and slower just because of how many image tokens and text tokens there are. Okay, so the teacher and at least two students are visible in the second image, while the first image with the traffic cone on their head shows only one person. So now we're at a point where we can upload images. Some models even accept videos and can reason over short videos, answer questions about them. Some models can even generate short videos that look fairly realistic. So, you know, compared to last year, this is a huge improvement over what used to be the state of the art. So now we're going to, in the rest of this class, take a look at how we get from images to these kinds of models that can process both images and text and generate either modality. Any questions so far? All right, let me make sure this is working on YouTube. Okay, I suppose it is. That's great. All right. So before we had things like ChatGPT and BERT and you know, large language models, back in like 2014 or 2015, people used to work on very simple image and text tasks. So image captioning is one of the first tasks that people worked on in this multimodal space. And the task is obviously quite simple. Like, we even looked at 2 instances of this task in our prompt. Given an image, we want a language model to generate a caption of that image. Right, so here I might have a red truck parked on a street lined with trees. I could also answer questions about the image like we did in ChatGPT. Is this truck considered vintage? Does the road look new? Blah, blah, blah. So to understand how we can even get to this point, we first need to understand how to represent images, right? So we know how to represent text, or we tokenize the text into a sequence of either words or subwords or characters or whatever. We pass those tokens into an embedding layer. We get these vectors, and then we have our whole transformer thing that predicts the next word, right? So what is the equivalent in image land? So first, let's take a look at a grayscale image, right? A black and white image. These are represented just with a single matrix, where each element here in this matrix is an integer from 0 to 255, as I just answered this question. So these are pixel values, right? So you can represent any grayscale image with such a representation. So you can see that an image, by definition, is just a matrix of numbers, right? So in text, we have words or characters as our basic unit, and we need some way to convert those into a numerical representation so that our big models can learn on top of that. But with images, we could potentially just learn directly on top of the image, right? There's no need for an embedding layer if the raw representation is itself already in this kind of format. So that's a grayscale image. A color image is generally stored as a tensor, so we have basically 3 different matrices here, and these are for different colors, so like RGB. There's many different color representations that you could use, but here each of these matrices can take a value from 0 to 255 in this RGB encoding. Okay, yeah, and there are all these other color spaces that could be useful depending on what task you're doing, and maybe some of these are more convenient than others. I think like lab, for example, I believe the L represents the intensity of the color, and the AB gives you the actual color value. Okay, so one of the critical components of computer vision, or models that are trained to understand and predict things over images, is this convolution operator, right? So if we're working with a raw image, let's just assume we have a grayscale image, right? It's a matrix. What we generally do is define a smaller matrix. We can call this a kernel, which the values here are generally learned. And what we do is we slide this kernel over every single pixel in this input image. And we perform basically an element-wise multiplication on the corresponding region of that image that is centered around a particular pixel. So if we've chosen this pixel, we will multiply this top left element here of our kernel with the top left thing over here, this one with this element, and so on. So we'll get 9 different products, and we will sum them up. And that sum gives us the value of the resulting output cell in that location. And so there's many ways that we can use this general framework of applying convolutions and shifting them over the image to influence the dimensionality of the output. So if we wanted a smaller output than the initial image, we could, instead of going over every pixel, go over every other pixel, and then we might get an image that's half as big. There are other approaches we could use. We could do what's called pooling, where we might look over here and define a block and take the max value of that block as what is actually getting stored in our output. So many different things, but the core idea is that there's this convolution operator that is generally very useful for image understanding. And why is this? This is just a 3x3 matrix, and our image here could be huge, right? It could be like 512 by 512. So what is this thing doing here? This is a very local operation, right? We're looking only at 9 different values at any given time. But the idea is that images themselves are quite regular at a very fine-grained level, right? They have edges, they have shapes, they have distinct patterns that appear at a very fine-grained level that can be modeled with these kinds of simple matrices. And so as an example of that, first we can do a quick demo, but I think it's pretty clear. So if this is our kernel here, or weight matrix for the convolution, and we're at this block here, the resulting value in this output image is, we'll just look at the non-zero elements. So this one is multiplied by 3, this one is multiplied by 1. We add them up, so 3 plus 1 is 4. 4 is what you get when you apply this kernel over this patch of the image. All right, so there's a demo here I wanted to show. Okay, so this is a grayscale image of a person. It's this tiny image over here that's been blown up to huge size. And so this is what happens if you apply this kernel over the entire image. So what is this doing? You can see that it is giving a high value to whatever pixel is in the center of this kernel here. And it's negating everything that's in the surrounding, like not in the center. So if you apply this image to the entire, if you apply this kernel over the entire image, you get the result of what looks like the image has been sharpened, right? Like the contrast has been increased, the edges are much more clearly defined. And so many like basic Photoshop filters can be implemented in this way with just these simple hard-coded kernels. We can try other kernels too. So let's see what blur does. So you can see the blur kernel is like kind of the opposite. It basically just assigns some small weight to every pixel that is in the region. So they all get averaged together, and as a result, you see an even more blurry image than what you started with. You can look at something else, maybe outline. Oh, God. Okay, so this one has just amplified the center and negated everything else, so you get something like this. So you can make pretty wild changes on the input image just by running these convolution kernels over the entire image and seeing what you get. That said, these are all fixed kernels, right? So this identity kernel will just give you the resulting image back. The idea behind convolutional neural networks is that we will learn the weights here, these numbers associated with each of these 9 elements. We will learn them through backpropagation. So these are going to be parts of the weights in our network. So if we come back to the slides, you can see here that this is a picture of Einstein, and we're going to feed this through 4 different convolutional kernels that's represented here. So if our input is a 224 by 224 image, our output is going to be a 4 by 224 by 224. So one of these 224 by 224 images for each of the 4 kernels that we have here. So as I mentioned before, if we wanted to get smaller outputs, we can skip over every other pixel. So that is a hyperparameter of this called the stride. So if the stride is set at 1, we will just go through every single pixel in the input image and make a corresponding output value. If the stride is set at 2, then you can see that our image is halved in size, right? So we get a different image. we can use these kinds of properties to get some sort of bottleneck representations that we can try and have the model learn through. All right, so the very first paper actually that made deep learning and big neural networks on large data sets made all of that popular was this AlexNet paper from probably like 15 years ago or so at this point. So this paper showed that whatever was happening in computer vision before then, which used mainly these kinds of handcrafted features or features that used heavy manual engineering, really underperformed just learning a big, deep convolutional neural network over a supervised data set. So this was specifically for the task of image classification, which you're given like an image and you're asked which one of like 1,000 different categories does this image belong to? So the categories could be like dog, cat, or other common objects that could be in the image. So we see here like there's different species of animals. There's things like banjos or barbells or mazes or whatever. So you were given 1.2 million images. They just trained a big network, and it got like much better performance than anything that had been seen until then, which kind of kicked off, okay, can we start scaling this up? Can we build different architectures and so on, which has continued to this day. But all of this stuff with neural network models was not happening in text at this time. It actually took a couple years from this paper till when people decided, oh, we can actually use recurrent neural networks and get really good representations of text. But part of the reason for that was because text is not so easily encoded into numerical form. So we needed to have advances like word2vec and things like that, where we actually, people figured out how to represent text with vectors first and then plug them into other neural architectures. So computer vision actually kind of birthed this whole like scaling big models trend that we see today. So this is the original AlexNet architecture. I'm just showing this as kind of a historical artifact at this point. Now, like you could probably train this on your MacBook in a couple minutes if you wanted. But I'm showing it also to compare with the architectures that are used today, which we'll see later are much bigger, deeper, and not using convolutions, but rather transformers. So you can see like you start with the initial image, you apply a bunch of convolutional layers, and the resulting dimensionality of the image is being modified until you get this point. And then finally, when you get over here, you feed it through some linear layers, or fully connected layers. Finally, you get a vector of 1,000 dimensions. You apply your softmax over this vector, and then you interpret that in terms of like the different 1,000 different classes here. So probability of it being like Abyssinian cat. All right, and people started to interpret or try to interpret what these convolutional layers were doing. And for computer vision, these networks are much more interpretable than for natural language. So we can actually see like what these different kernels are doing at each layer. So at the lower layers, we see some of these kernels are like detecting edges or different orientations of edges. Then as you get higher up in the network, we start to see like combinations of edges. And finally at the top, like more concepts and objects that are being activated by these layers. So a lot of the interpretability work in neural networks is, I guess, most useful for image-based neural networks. Okay, and then we see this plot, which shows you how in computer vision people scaled this simple idea. So this AlexNet was a tiny model with 8 layers. And then for a while, people scaled up to 19 layers with this VGG model in 2014. That was widely used for a couple years, and then, well, maybe less than a year, and we got 152 layers. This was alongside the ResNet paper, which introduced the residual connections that we learned about in transformers that really allowed the scaling of really large, deep networks that before then we couldn't scale due to difficulties with the gradient flow and so on. Okay, so nowadays people in computer vision have shifted over to the transformer to encode images. So let's take a look at how that works. One thing you can think of doing is just vanilla taking the pixels of the image. As you see here, well, obviously this is not just 9 pixels, but let's say that we had this image here with 9 pixels. We can linearize it, right? So you can see here that the top row is the first 3 pixels, middle row, next 3 pixels, bottom row, last 3 pixels. Now we have a sequence of numbers, right? So we can just feed that into a transformer, do self-attention, stack the layers, and finally we can predict the class of this image. So that is actually what people have tried early on. You can actually devise a language model out of this, where here is your input, and you feed it into the transformer, and you're trying to predict the next token or the next pixel. So here, given this like start of sequence token, you predict the next value. Here, you're trying to predict this blue value. Here, you're trying to predict this dark blue value, and so on. So very similar to text, except your targets are not words or tokens, but rather the value of the next pixel. You can also do this in the masked language modeling setting, right? You can take one of these sequences, you can mask out different pixels, and then ask the model to predict what is the missing value here. So what are some issues with this setup that you can think of? Like just taking an image, converting it into a single sequence of pixel values, and then doing next word prediction on that sequence. That's a good point. So if we do this, right, then we kind of make it difficult for the model to recognize that this whatever olive green pixel is right below this one, right? Because now it's 3 tokens away, even though in the image it's right below the, but the model could potentially learn this, but it needs to handle longer range dependencies, right? What if the image was a lot bigger? This kind of modeling might become more difficult. So that's a good point. Any other issues? We would lose depth perception. I mean, I would say it could, in theory, if it is a very good model of the next word, right? Then even though we made it difficult in terms of the order of the pixels, if it is good at predicting the next value, then perhaps it could overcome all of these challenges. But yeah, that is certainly, like, flattening the image into the sequence does pose some problems in this way. Any other ideas? Mm-hmm. Yeah, so since we're modeling the raw pixels here and we don't have any explicit convolutions, it might be hard to learn these like shared occurrences of different things. On the other hand, it could be possible here as well. Like if you have a very deep transformer network, maybe some of those QKV computations could start to resemble convolution at some point. But yeah, it might not be the right architectural choice here. All right, one more. Yeah, right. So if we have a very large image, then this is just not going to scale, right? Like, it's fine for a 3x3 image, but what if we have like 1024 by 1024? This kind of linearization is just going to break, right? At least we would need huge memory requirements and probably better architectures to take advantage. Okay, yeah, go ahead. Mm-hmm. Right. Yeah, so it is a little less clear if next pixel prediction is a meaningful task, right? And again, it might be very locally dependent, just like in language, except even more so. Like if I know that this tongue pixel here is red, and I'm trying to predict the next pixel, I may not need to have any knowledge of the rest of the image in order to do so. Okay, so let's take a look at like probably the dominant architecture for images now, which addresses somehow some of these problems that you brought up, but not all of them. And this paper, An Image is Worth 16 by 16 Words, was from iClear 2021, and they proposed this architecture called the visual transformer, which in various different configurations is now kind of used today. The basic intuition is you take an image and you split it into patches. So now you're not looking at each individual pixel here, but rather patch, and in their setting, a 16 by 16 patch. So now you have each, here we have, let's say, 9 different patches in this cat image. Each of these 3 by 16 by 16, so the 3 is for the RGB, the different channels in this image. So 3 by 16 by 16 is not that big, right? So you take the pixels here, you can linearize it and then pass it through a linear layer just to reduce the dimensionality of each of these patches. So they also add these position embeddings here, where with these position embeddings, you can get a little more fancy than the ones for text. Like you could try and encode both the row and column dimensions into the position embeddings if you like. They didn't do anything like that, just had learned position embeddings. So basically here you have 3 times 48, so each of these is pretty small. Like you can think of it kind of like an embedding of that patch, except it's just the pixel values. It goes through this linear projection, it gets position embeddings added to it, and then you have the transformer that we learned about, exact same thing that we use in text, no differences. You get the final layer token level so here it would be the patch level representations. And instead of predicting the next patch, whatever that means, they just train this in a fully supervised way on the ImageNet data set. So the goal is, given this image, I want to predict that it's a cat out of those 1,000 different classes. So I can just put a softmax layer on the very last hidden state here to get to a 1,000-dimensional probability distribution, and try and train this model such that the probability of cat increases. And I can do this on millions and millions of images and get a very powerful transformer encoder of any image. So the basic steps are take an image, divide it into patches, and then proceed with transformer model training. Right, so you have these 768 dimensional vectors here. So in comparison to that 152 layer convolutional neural network that we were talking about before, it turns out that as you scale up the size of the data set, so here this data set had 300 million images labeled with one of those 1,000 different labels, you can see that the transformer starts to outperform all of the other models. And it also has many benefits of, that we got in text, right? So the transformer, you can fully parallelize everything at training time, and all of the tricks we've learned for text language modeling can carry over to this setting as well. So basically, people are using these kinds of encoders that are patch-based for images, and then obviously we're using all the models that we've learned about previously for text. And there are a lot of similarities, right? They're the same backbone architecture. Really, the only difference is in the input, like how is the input being represented? Is it like subword embeddings, or is it patch embeddings? And what is the training objective? Is it to like predict the category of image, or is it to predict the next image, the next word or next patch? But the large majority of the architecture is identical. So people have obviously observed this, and now there have been many efforts to train joint models, right? So you have a single model that can process both images and text. And you can imagine a very simple case where if the input is an image, you can convert it to patches and use the same steps down here to get a sequence of embeddings. If the input has text, we can just get the token embeddings, make sure they're the same dimensionality as these, and treat them all as one big sequence. So if I have an input that has interleaved text and images along, I can get a single sequence that is tokenized to include vectors of both modalities, and then do some sort of learning on top of that. So that's the general idea. And so we've seen like many of these encoder-based models crop up where the input can be either image or text. So OpenAI's CLIP encoder is probably the most popular of these kinds of models. Basically how it worked is they collected a huge data set of image-text pairs from the web. So these could be like the alt text of an image, or like an explicit caption or something like that. You can just crawl these from the web or from Flickr or whatever kind of image hosting data sets there are. And then they decided to train two different encoders. So one for the image side, one for the text side. But then through the objective function, they kind of encourage both of these networks to use a shared representation space for both images and text. So the idea is this. Let's say you have a batch of images and they're paired with their corresponding captions. So this top image here is paired with the caption or description, Pepper the Aussie pup. And similarly, let's say we have many other n different images and corresponding texts. So here, the loss function is, first, I feed each image into the image encoder to get an embedding, I sub 1, I sub 2, I sub 3. Then I also do the same thing with my text encoder to get a text embedding, T1, T2, T3. And I compute the dot product of each image vector with all of the text vectors in the batch. So I1.T1 means we're taking this image of the dog and this text, Pepper the Aussie pup. The goal is to make this dot product as high as possible. Like, this is the ground truth caption of this image. I sub 1 dot T sub 2, however, is this image with a completely unrelated caption, like whatever is second in this batch. So we want to minimize this dot product. And so if you think about this entire batch, all of the elements on the diagonal are the dot products that we want to maximize, and all of the off-diagonal dot products we want to minimize. So you get this very simple loss function that uses contrastive learning to accomplish this. And the biggest hyperparameter here that is the most important thing is the batch size. So if I have a very big batch, then it becomes a lot harder to have a high dot product here and a lower one everywhere else. I might get more images that are similar to this, dog. Like I might get another dog, right? And I have to actually somehow differentiate the, like, where the dog is from or some other components of the image that make it such that only this dot product should be high and the others should be low. So if you have large GPU resources, you can really scale this to huge batch sizes, and as a result, you get this this model. Yeah. Yeah. So think about it this way: like each batch, let's say here, consists of n different image text pairs. So at index 1, I have this dog image and this caption that is the ground truth caption for the image. However, I sub 2, I sub 3, I sub 4, these images are unrelated to the caption at index 1. So you can think about it like you have these paired image text examples. The diagonal represents like I1, T1, I2, T2, I3, T3. These are all the correctly aligned images and their corresponding captions. Any other off-diagonal element is unaligned, like it's either the wrong image or the wrong caption. Yes, you have to make sure that's the case. Yes. Other questions? All right, let me check on YouTube because I am. Oh, yes. There are many different loss functions, but you can imagine. Okay, I'm sorry about that. Oops. Back here. So you could imagine doing something like a softmax here, where like for each example, each row here, only this dot product should be, say, 1, and these should all be 0. So you can imagine losses that are similar to that. But yeah, there are many different ways that you could do this over the whole batch as well. But that's the simplest. Other questions? Okay. So they train it in this way, and then they find that you can actually use this to do some sort of zero-shot learning. So you can create, like, if you know what labels you're interested in, let's say here they say plane, car, dog, bird, they're able to generate encodings of all of these words using their text encoder. And then if you have a new image and you want to classify it into one of these categories that you've set up, you can simply just get the image encoding using your image encoder and then take the dot product with all of the text classes that you've come up with and pick the one that has the highest dot product as the label of this image. So this is obviously much simpler than what is happening in GPT-4. GPT-4v can actually generate text that is about the image. So we'll take a look at how that happens now. But this is probably the first approach that used like huge scale training in order to get high quality representations of both images and text that could then be used to solve like novel tasks with just those representations. Okay, and one advantage of this that they found, which could be like largely a data set issue because they trained on data from the web instead of just this ImageNet data set, is they had like all these other kinds of cartoon images or sketch images where previous models were not very good at detecting that, for example, these are bananas, because it's not like a photograph of the banana, right? It's a sketch. It has a different style. But the CLIP model is actually quite good at recognizing that because it's seen a lot of these kinds of images in the web training data that it had access to. There are also these adversarial images here. So this is like in the, I think generally like they're objects that are in situations where they don't really look like the object. They can fool the, as you can see here, the previous ResNet, the convolutional net, was getting 2.7% accuracy at, for example, saying this is a banana, but the clip model is much better at this. Just a data set thing. And so obviously, as the years went on, people have been gathering larger and larger data sets. This Lion 5B, has 5 billion image text pairs that are crawled from the web. They basically took the Common Crawl, which is one of the most popular data sets for text training. It's just a dump of the internet, like various websites. Those websites also have images in them, right? Like a random web page. So you can take the image off of the website, get some corresponding text from that website as well, and do a lot of filtering to get that into a highish quality data set. I should note that there's a lot of copyright issues with this data set. There's actually a lawsuit that people filed against, I believe, Stable Diffusion, who used this data set to train their models. There's a lot of stock photos and things that are licensed that are just in this data set. And of course, creators of those images want some sort of compensation for this. The lawsuit is still ongoing. I don't know what will happen with that, but as part of that lawsuit, OpenAI and others also got sued because, like authors of text also want some compensation for the inclusion of their work into data sets used to train these models and then make money. So we'll see what happens with all of that. It seems like, copyright law will probably need to be modified heavily to include, consequences of AI training on data. So this was the text of the lawsuit. Most of the images contained in the data set are copyrighted. So we'll see what happens. Okay, so in the rest of the class, I wanted to go over some more recent work that kind of unifies transformer decoders with image encoding. So I'll start with this Fuyu 8B dataset model from Adept. Some of these companies don't really release papers with any details, but they prefer to just do blog posts. But I think this one is a good place to start because it does have a very simple architecture to enable like generation on top of image plus text inputs and generating corresponding text. So they have this figure here that I wanted to show you. So they have this picture of a persimmon, and just like we learned about, they split this image into patches. And then each patch, they use just a simple linear projection to get it into a vector representation. As some of you noted, you will still have this problem if you're using patches that, this patch and this patch are kind of far away from each other when you do the linearization. So they actually decided to add a special token at the end of each row of the image, like a image new line character that indicates that we're moving on to the next row. Probably this is useful in guiding the model to attend from this patch over here more closely to a patch right after the new line character. But the interesting thing is that they side by side also encode the word embeddings associated with any language input to the model. So this says this is a Fuyu persimmon, and here you can see that they actually have their training objective, which is language modeling on the text side. So basically you get the image patches and you encode them into a vector. There's no loss function here. And then once you get over here, at the end of the final image new line character, you start predicting the image caption in natural language. So this is a Fuyu persimmon. And in this way, you can learn a model that can take images as input and do like QA or captioning or whatever you might want to do on top of that image. Does that make sense? So it's a very simple architecture, but this model does have some competitive performance with models of the same scale. Yeah. Yeah, that's a great idea. So I think your suggestion is just like alibi, you could just do some linear bias on top of these patch embeddings that, again, encodes like both the row and column difference. Probably it's just a difference in how many. Yeah, that would be cool to do. I'm not sure if it's been done. I suspect it has, given how much work there is in this space, but I don't see any reason why it would be a bad idea. Yeah. Generally, the patch size is fixed to like 16 by 16 or something like that. The number of patches can vary depending on the size of the image, but in general, like very high resolution images are usually downscaled to some fixed size and then like patchified, just to whatever the compute requirements are, or whatever was done during training. Yeah. Well, oh, that's a good question. So the question is, like, how do we even train this image encoder given there's no loss over the image? But note that the next word prediction on the language side is a function of these image representations, right? Because we are doing self-attention over every part of the sequence. So during backprop, like, if the model is going to generate a meaningful caption of the image, it has to know what is in the image, right? So these inputs are critical to determining the content of the caption. So during backprop, hopefully the model, just through the language side prediction, will learn how to reason over the image. Yeah. Yeah, that's right. So this model can only do things in the text side. Models that do image generation do generate, like, they can do next word, next like patch embedding prediction. Basically what you do is you develop a vocabulary on the image side. So you can imagine like essentially clustering the patch embeddings. That is the process, although it's more complicated than that. You can learn a vocabulary and then just do next word prediction over the image tokens. And this is what is generally done for the models that can actually generate images as well, like DALL-E and Midjourney and so on. Yeah. Yeah, so is your question like the images that are generated by these models, I guess, are not completely realistic looking? They have a, yeah. I would suspect the vocabulary size and way it was created is part of that, but they have been getting a lot better recently. So I'm not like, you know, OpenAI doesn't really tell us how their model works at this point. So it's not clear if they have a better technique of, or maybe they're using a bigger vocabulary or a better method for generating that vocabulary, or something else that they're using. Even Midjourney's models are closed as well, so we don't really know what improvements they're making. Yeah. Yes. So imagine in this case that these linear projections, the output of these projections are of the same dimensionality as your word embeddings. So there's nothing that implicitly says that these should be in a different space, right? Especially if they're getting trained using the same objective that is trying to basically increase the likelihood of the test response, right? So the idea is that you know, they don't have to be in the same space, but the model will have to learn how to reason over the image tokens and the text tokens to like increase the likelihood of the correct response. Yeah. That's the idea. So if you have no image input at all, the model should still work. So here, like during training, you can also train with no images, right? You could just take Wikipedia or something and train the text side of the model as well. Again, it's not really clear what this company did for their model, but the figure is quite instructive, I think, of many different possibilities. Yeah. So remember here the patch, let's say it's 16 by 16 patch, so there are 3 channels, so you get 768 dimensional vector for each patch with just the like raw pixel values, right? This vector is then just fed into a feed for like a linear layer to whatever dimensionality they want the model's internal dimensionality to be. Yeah, yes, that's right. Every part of this is being trained through the next word prediction loss on the language side. Okay, great. So I see no questions here. The last thing I wanted to do is look at a cool blog post that was recently published on Hugging Face, where they're looking at one of the major issues with all vision language models currently, which is this problem of like if there is something that is kind of small in the image, they won't be able to reason over it. Like we saw in the first example, I asked how many like legs are on the man's shirt. It wasn't able to do that reasoning. Here, this is an example where the author of this post asked what is written on the sign in this photo, right? So the sign is over here. It says like core power yoga, live power upstairs, something. But obviously it's like kind of hard for us to read it, and it's a very small part of this image. So if you imagine you're dividing this image into patches, there could be many issues here, right? Like you might not get a patch that is directly centered over this image. It might be split into 2 patches, the sign. And you know, there might be a lot of other parts of the image that are taking up more real estate and similarly get modeled, get the representation might have more stuff about trees and plants in it than anything to do with this sign. Right, the image has this, it's a pretty big image, high-res image, but the blog post says these models can't zoom in. They're limited by the resolution of their image encoder. So a lot of these high-res images are resized before they're fed into these encoders and then patched. So here is the resized image. We can't really see what happens here when it's been downscaled to this resolution. So the author tested like a bunch of these state-of-the-art models on whether they can read what's in the sign. This one says it's a pizza shop, so that was obviously wrong. This one just says chrysanthemum. And this one says it's a cafe. So like a reasonable guess, but clearly it wasn't able to read the image. And GPT-4V says, I am unable to extract textual information from images. Clearly false, but whatever. So none of them could reason over the text in this image. And some of the solutions that are in this blog post, which I linked on the website, are pretty interesting. So this one, I think, is at least conceptually quite interesting. So if you have this similar construction here where you have an image and you want to ask a question about something that's a small part of the image, first you might want to identify where the glass is, right, before you start to answer this question. So all of those previous models just take a full representation of the entire image and try and reason over that, where instead maybe we first want to seek or like crop the image that is relevant to the question and then answer it. So they have, like, instead of trying to give an answer, their model generates some initial response. I need to find the glass first, and then it like seeks over different objects that are in the image using various techniques like object recognition, and at some point it finds this bounding box around a glass that's in the image. And at this point, it can feed this image into the model and then extract the answer. So this is something that people have been doing in this multimodal space for a while. We used to see like attention, like visual attention over the image, where to answer this question, you might, again, like divide the image into patches and then do attention over the patches, get a new representation of the image weighted by the query-based attention, and then finally generate an answer. But it's cool to see it happening with these giant models. This is a similar technique where you have some way of first cropping the image before you extract the representations to answer the question. Yeah, and more things like this. So yeah, that I think is one interesting way to proceed. There's also like this distinction between models that are trained to be multimodal inherently, like we saw with this model. Both images and text are combined into a single sequence, and the model is trained on top of that, versus these kinds of hybrid models where you first train an image encoder, you train a language model separately, and then you learn some adapters or something to combine both of them. So GPT-4V, for example, although there are no real details on how it works, it's likely using their giant text model and a powerful encoder like CLIP, and then figuring out how to fuse those two components together rather than being trained from scratch like this Fuyu model here. So yeah, I think I would have liked to talk about video, but it's not really at the stage where things are working just yet. So maybe next year for that. But hopefully you have some understanding now about why like computer vision and NLP are kind of becoming one and the same. The models are literally the same, right, at this point. And so moving forward, we're going to see many more multimodal models. Can't really say language model, right? Like vision language model, video language model, that are trained in a similar fashion to this, and you know, that should lead to a lot more grounded language processing abilities. Okay, any final questions? Yes. Yeah, so generating images is, I believe, quite similar to in text, because you are first, you're not generating the actual pixel values directly, but rather you're generating tokens in a vocabulary that has been learned on top of those pixel values and patches. So it is, you can use a transformer decoder to do that process as well, provided it's been learned on enough images and your vocabulary is good. So there are techniques like the VQ, VAE. This is a popular autoencoding technique that is used to learn, like induce a vocabulary of visual words that you can then predict. But yeah, you can use the same architecture and training objective to do that. It's not at the pixel level. I believe it's at the patch level, but I'm not actually sure like what the dimensionality is. Yeah. Yeah, that's a good question. I'm not actually sure what the if they did ablations on the patch size. I would say they probably weren't able to, because for each different configuration of the patch size, you need to train a whole new model, right? Which is incredibly expensive. So I suspect that like people have been using the pre-trained models that have been released with like 16 by 16 patches or something like that. With smaller patches, maybe you would be able to get away without doing any of these like search or crop types techniques, but the sequence length will also get longer in those cases, which is important consideration for inference. Yeah. Yeah. Yeah, I mean, these are just techniques for localizing important information within the image. Yeah, the resolution will still be an issue, so there might be other techniques that you could use. Yeah, it kind of just makes it easier to answer these questions. It does not solve this issue. So I guess that's a, yeah, a hyped up title there. Yeah. Yeah, so all of those like applications that you see like in today's Photoshop, you can even just highlight a region and type in like change the background to a blue sky or something, and it can do that. Yeah, I believe all of those are using these like visual word prediction type systems, which are again just transformer decoders that are predicting in a different vocabulary. Yeah. All right, so next time we have, I guess, two orders of business. So first we will cover the midterm, and then we will try and go into an in-depth exploration about in-context learning. So like, how is it that I can just give GPT-4 like 3 examples, input-output pairs of a task, and it can learn how to perform that task even if the task was not present anywhere in its training data before. Like what kind of mechanisms make that possible? And there's some interesting theories there. They're not proven or anything, but some compelling evidence for different mechanisms that enable in-context learning that we will talk about next time. So see you on Wednesday.